All right, so the rest of the sections of this chapter I would have to say are the most important for your semester. Sections 1.7 through 1.10, you are going to use the entire semester, guaranteed. So if there's something that you think you need to master, these sections are it. Now, as a chemist, I often make measurements every day. These measurements are used in calculations for certain experiments or any other related activities. There's lots of different ways that I can measure things, and you are probably aware of that because sometimes we want to take the length of something, so we use a ruler, or we want to weigh ourselves, so we go on a scale. And you have probably also realized that a measured quantity is associated with some sort of unit. For example, I like to ask my students, how tall are you? And students usually answer with some sort of answer similar to, well, I'm 5'5". And then I precede that answer with, well, 5'5" what? Are you 5'5" acorns? 5'5" squids? Not really sure what you are. And then they start laughing and they say, no, I'm 5 feet 5 inches. Oh, okay, now I understand. So it's a silly example because we all know here what we mean by 5'5", but what if I wasn't from this country? What if I used different units and I thought you meant 5 inches instead of 5 feet or 5 centimeters instead of 5 feet? So it's very important that we include units with our measurements. I am a stickler for units. So in your exams, you will have to be very careful when you write down answers without units. You will get them wrong. So the units that we use in chemistry are called SI units. You might know them as metric units. The more familiar units in the United States are English units. Examples of the English unit would be a pound, a foot. Examples of the metric units would be a meter, a kilogram, a second. Now, the table that I am showing you here, table 1.2, describes metric SI base units for the length, mass, time, electrical current, so on and so forth. These are the units that we will be using in this class. If table 1.2 is important, then table 1.3 is 100 times as important. This table you need to memorize, but you don't need to memorize everything. All you really need to do is learn the prefixes and the meanings, but only this part of the meaning. Now, it might seem a little daunting, but what I like to do is I like to make a song or like a story for it that'll help me remember the prefixes and their meanings. Now, if you start from tera and you end up at attomoles, which you don't see in this table, I made up this saying, which goes like this. The gooey monster king died, carrying million microscopic nomads for attorneys. Now that works for me. Usually if you're going to remember something, you have to make it up yourself. So I encourage you to make up your own little funny story to remember these. So like I said, the important thing to remember is the prefix and the meaning as far as 10 to the 12th, 10 to the negative 9th, 10 to the negative 1. Those are the most important things that you need to know. And you will be using these in dimensional analysis. Section 1.7 also goes over certain terms like mass and weight. You need to know the differences between these two terms and be able to explain them. A good way to find out whether you understand it is ask yourself, do these gold bars weigh the same on Earth than they do in outer space? Do these gold bars have the same mass on Earth than they do in outer space? The mass of something is constant. Weight changes depending where you are. The actual definition for weight is the force that gravity exerts on an object. There is more force exerted on us when we're on Earth than there are when we're in outer space. So that's why we weigh less in outer space. The remainder of section 1.7 goes over volume and density, as well as temperature, but let me concentrate a little bit on density. You are going to be responsible for knowing what density is and what are the units of density. Density is defined as mass divided by volume. The units that we use for density are usually grams per milliliters. If you look in table 1.4 of your book, you'll see some common substances and their respective densities. Notice that the unit given in that table is grams per centimeter cubed. A good exercise is trying to figure out how to convert centimeter cubed to milliliters. That is a very simple problem, and you should be able to do that. All right, so now I'm showing you 3 thermometers which display the 3 different temperature scales. We have Kelvin, Celsius, and Fahrenheit scales. Your book gives you equations on how to convert between the 3 different scales. You are responsible for knowing those. I have a question for all of you. Do you know how a thermometer works? I mean, it's very simple. The basic premise of a thermometer is that things expand when they're heated and they contract when they are cooled. Think of a balloon. If you were to put a balloon, fill it up with air, and put that balloon inside your freezer, what do you think will happen? That balloon will contract. And if you take that balloon, don't do anything to it, but just take it out of the freezer, what do you think will happen? It will expand again. And thermometers work in the same manner. So the liquid inside the thermometer is expanded when it's heated. And when it's cold, that liquid contracts. Have you ever thought about bridges? Bridges are made up of usually iron or steel, but those materials also expand and contract when heated or cooled. So have you ever thought about how is it that bridges are connected to land? If there is such expansion and contraction happening, how are they connected to land constantly? It's a very good question to think about. As I mentioned before, you are going to be required to be able to convert between one temperature scale and another temperature scale. So make sure that you practice that at home. You should also start to practice how to convert units. Converting units is something that we will use the rest of the semester. And that's the main topic on our next video module.